Well, hello and welcome again to our journey into algebra and number theory. And in this little section, there'll be 3 videos in this section. We're going to look at some applications of some of the ideas we've been developing in earlier videos to some number theory. I'll begin by having a look at general Diophantine equations, just to say a little bit about these. They're named after a Greek writer called Diophantus, of whom we have 6 of his books surviving from antiquity, which are really just problems and how to solve them. There's no general theory in his writing, but they're very interesting, and some of the solutions are very clever and very intricate. And in fact, it's those books that motivated later mathematicians such as Fermat and Euler. Fermat in particular worked through Diophantus and tried to understand some underlying principles and develop some theory that to explain some of what Diophantus was doing. So in his honour, we call Diophantine equations are equations where we seek integer, sometimes only positive integer, solutions. Sometimes one looks for rational solutions as well, but generally we're interested only in integer or positive integer solutions. So a very well-known example of this is x squared plus y squared is z squared. It's a famous Diophantine equation, and this one of course has infinitely many solutions, because if you take the we have infinitely many triangles with right angle triangles with integer sides, and they will satisfy this equation. So the famous 3, 4, 5, for example, 3 squared plus 4 squared is 5 squared, and 5, 12, 13, 5 squared plus 12 squared is 13 squared, 9, 40, 41, and so on. And this has infinitely many solutions, and in a later video we'll actually find a formula for generating all of the solutions to this Diophantine equation. Sometimes Diophantine equations have no solutions, and sometimes they only have finitely many solutions, as in the next couple of examples. So here's a Diophantine equation: 2x squared plus 5xy minus 12y squared is 28. And this has only finitely many solutions. And the way we can see that is that think of this as a quadratic in x, and try and factorise it. And you quickly discover that this is a factorisation of the quadratic here, and it's got to equal 28. Well, now unique factorisation kicks in, and we've got 2 numbers multiplied to give 28. There's only finitely many cases, and I've listed them all here. So there's the first number, and there's the second number, and so we could have 28 times 1, or other way around, we could have 1 times 28, or we could have 14 2s are 28, or 2 times 14, or 7 times 4, or 4 times 7. And we could have all the negatives of these as well, because we're interested in integer solutions. Now when you then put these expressions equal to each pair and try and solve the simultaneous equations, you find most of the time you get fractions, you don't get integers, except you get these ones. You do end up with 8, 5 and minus 8, minus 5 as being solutions. So this Diophantine equation has only 2 integer solutions. So that's an interesting example of one of these Diophantine equations. This one here is slightly different. We've got x squared minus xy plus 2x minus 3y is 11. Now here again, we're going to make y the subject of this. This doesn't factorise nicely. We've got a y, no y squared, so we've got a y here. So we can make y the subject of this, take all the terms with x's on the other side and factor out a y. We can then divide by x plus 3, and we end up with this here as the y formula for y. I can then do long division on this, and when we divide the quadratic by x plus 3, we get x minus 1 minus 8 on x plus 3. Now y is a whole number, this is a whole number, so this has got to be a whole number, and that means x plus 3 has to go into 8. It's got to be a factor of 8. And so there are not too many factors of 8, there's only plus or minus 1, 2, 4 or 8. And solving that then for x, we end up with these 8 solutions here for the Diophantine equations. So this one again only has finitely many solutions. In general, Diophantine equations are very, very difficult to solve. We're only going to look at certain special cases here, and in particular we want to look at linear Diophantine equations because they're very easy to solve. So these have the form in two variables, and it generalises, of course. We're only going to look at two variable case. Ax plus by is c, where a, b, c are integers, and we seek only integer values of x and y. You can think about this geometrically, by the way. This represents a straight line, and so we're asking, are there points on this straight line with integer coordinates, is another way of thinking about this problem. Now sometimes this equation will have no solutions. If it's got solutions, it turns out to have infinitely many, and we'll actually write down how to find them. So observe, for example, if I look at this equation, 3x plus 9y is 5, then the left-hand side is divisible by 3, but the right-hand side is not. And so this equation cannot have any integer solutions. It doesn't make sense to have integer solutions. So just observing this, the biggest number that goes into both of these, the GCD of these two numbers, is 3, and 3 doesn't divide 5. And so we perhaps feel a theorem coming on. And here's our theorem. We've got a, b, c is our integers, a and b not 0. Then if d is the greatest common divisor of a and b, then ax plus by is c has solutions if and only if d is a factor of c. We might have guessed that you need d to divide c to have solutions, but the fact that if it does divide c, you always have solutions is a nice fact. And here's a little proof of this. So let us suppose our greatest common divisor d is a factor of c. So I can write c as some multiple of d for some integer k. Then by our theorem 6, that was our Bezout identity, our Bezout's lemma that we had back in the first section of these recordings, we can write the greatest common divisor as an integer linear combination of a and b. That is, we can write it as ax naught plus by naught for some integers x naught, y naught. So I'm going to multiply both sides of this by k. So k times d, we saw up here, is our c, and I multiply this by k and this by k, and I just judiciously bracket these terms together. So this now gives me a solution of a times something plus b times something is c. I can put my x then as kx naught and y is ky naught, where the k is the number we got from here, and the x naught, y naught are the numbers we get from Bezout's lemma, which we get from Euclid's algorithm, of course. And that will be a solution. So that proves then that if d is a factor of c, this equation always has solutions. For the converse, well, that's a bit easier, because if d doesn't divide c, then it doesn't divide the right-hand side. But this is impossible because d does divide a and does divide b, and therefore does divide the right-hand side. So we get a contradiction. So if a linear Diophantine equation has solutions, we can find them using Euclid's algorithm, since this enables us to write the GCD of two numbers as an integer linear combination of the numbers we start with, the a and the b. And we'll have a look at some examples of this. So we're going to find a solution to 3x plus 2y is 10. And by the way, you just quickly check the GCD of these two numbers is 1, and 1's a factor of 10, so we know it's got solutions. So we apply Euclid's algorithm to the numbers 3 and 2, or you can just use common sense. 3 minus 2 is 1. So 1 is 3 times 1 plus 2 times minus 1. So that gives me my x naught, and there's the y naught. So I'm going to multiply, this was 1, I'm going to multiply both sides by 10, and that'll give me 10 is 3 times 10 plus 2 times minus 10, and there's a solution. So we have x is 10 and y is minus 10. these are possible solutions. Well, these are in fact solutions. There are other ones as well. We'll see how to get them all shortly. If the GCD is not 1, then it's often useful to divide the whole equation through by the GCD, which has to divide the right-hand side anyway, otherwise there's no solutions, and then we can apply Euclid's algorithm. So for example, if I've got 12x plus 8y is 40, the GCD of these two numbers is 4, so I'll divide everything in sight by 4, which gets me back to here, and that's the one we just solved a minute ago. So this procedure gives one solution to the linear equation, and to get all the solutions we have our second theorem, which is a very nice result. If a and b are relatively prime, firstly, and x0 and y0 is a particular solution of our linear Diophantine equation, then there's the set of all solutions. So you take x to be x0, the one you get from Euclid's algorithm, your particular solution, plus b, that's the b multiplying the y, b times t, and y is the y0 minus a times t, where t is any integer you like. And this gives all the solutions. Now, quick little proof of that. If x0 and y0 are solutions, then immediately we have this. So if x and y are any other solutions, so that means we have ax plus by is c, then I can subtract these two equations, and I get a into x minus x0 plus b into y minus y0 is 0. Now the GCD of these two numbers is 1, so I can move this one term on the other side and say, well, the GCD of these two is 1, so that means the b cannot divide or have any common factor with a, so the b has to be a factor of x minus x0. Now if b is a factor of that, then it's just t times, then this expression here is just b times something. So x minus x0 is bt for some integer t, and there's our first formula. And we can just back substitute, and we'll get y is equal to y0 minus at, as we had up here. So note that we needed a GCD of a and b to be 1 to get all solutions of these formulae. Thus the first step in solving this is to divide the equation through by the GCD. You can get more general formulae for doing this if the GCD is not 1. It's just as easy to divide by the GCD, and that's it. So I'm going to solve this one here, and again Euclid's algorithm here, I need to write the GCD of 5 and 7 is 1, so I need to write 1 as an integer linear combination of 5 and 7, and Euclid gives 15 minus 14 as 1. So I multiply both sides by 37 now. So we multiply 3 by 37 to get 111, and 2 by 37 is 74. It's 37 here, and that from there I can read off my x0, y0. So we were looking for 5 times something plus 7 times something to give me 37, so I can take an 11 and minus 74. The general solution then is just y is 111 plus 7t, that's the b, and then minus 74 minus the a, that's 5 times t. And these give all the solutions. Again, you might like to think about this geometrically. This represents a straight line, and this is giving me all the points on the straight line with integer coordinates. Second example, we've got 12x plus 8y is 72. Now this time the GCD of these numbers is 4. So I'm going to divide everything by 4, which reduces it back to here. This one here, it's easy to check, has solutions 18 and minus 18. So the general solution then is 18 plus 2t, the 2 comes from here, minus 18 minus 3t, the 3 comes from there. If we wanted positive integer solutions, that is, so in this one here it says solve is in the non-negative integers. So if I want x and y to be bigger or equal to 0, then looking at the inequalities we get here, the t has to be less than minus 6 and bigger than minus 9. So the only possibilities then are going to be minus 9, minus 8, minus 7, minus 6. If you plug those in, you end up with these 4 solutions here. And again, geometrically, this is a line which cuts through the first quadrant, and these are the only points in the first quadrant and on the boundary which have positive coordinates. Finally, I just mentioned if a and b are positive, then we can solve ax minus by as c. All we do is we just replace b with minus b in all of the formulae above. And that's the end of the first recording for this section.